Hi everybody, I'm Ty Fredericks from Orchid Academy High School in Orchid, California, and this is NASA Now.
What that does on the asteroid, the astronauts read out the gravitational effect of those planets.
Hi, I'm John. You might be surprised to discover there is more to NASA than space exploration. In fact, chances are the planes you fly on today contain technology that was developed and tested at NASA. In this episode, we will talk with an expert about the special testing facility NASA uses to improve the performance and efficiency of jet engines. That's ahead, but first, here's what's happening at NASA now.
A flying dragon resupplies the International Space Station and breathes life into new discoveries. Well, not exactly. But on March 3, 2013, NASA and SpaceX successfully docked the Dragon space capsule to the International Space Station. This is the second in a series of efforts by the U.S. to transport supplies to and from the station since the shuttle's retirement. The uncrewed vehicle delivered more than 1,200 pounds of supplies and research experiments and personal items to the Expedition 34 crew. Dragon is expected to return to Earth on March 25th when it will splash down in the Pacific Ocean off the coast of Baja, California. Inside, it will bring back more than 2,600 pounds of science samples and educational activities. The knowledge gained from these materials is expected to expand NASA's capabilities for future long-duration space missions.
Every day, NASA is advancing our capabilities in space. At the same time, NASA is working on making air travel safer and more fuel efficient. Today we are going to visit Quito Thomas, a test operations engineer at the NASA Glenn Research Center. Quito works in the Propulsion Systems Laboratory, where some of the most sophisticated jet engines are put through extensive testing.
Welcome to the Propulsion Systems Laboratory, cell number 3. The Propulsion Systems Laboratory is an engine test facility where we test jet engines and we simulate the conditions that the actual engine or aircraft would see while it's in flight. We simulate altitudes from sea level up to 90,000 feet. We can test jet engines ranging in size from that of a small engine that goes into a RC aircraft up to a military jet engine that goes into fighters. We're able to vary the temperature in the facility to simulate altitudes. The air at ground level on a day like today is currently 60 degrees outside. Above 36,089 feet up to say 70, 80,000 feet, the temperature will be minus 40. We can go from Mach of 0, which is the air that we're breathing currently, up to Mach 3. The reason for these facilities and for the tests that we run here are that it's more cost effective to run a jet engine in these conditions because the conditions are set and they are fixed. Here we're able to set an altitude, hold that altitude, hold the temperature, and we're able to put a lot more instrumentation on an engine here versus putting it on an aircraft where you're limited on how much you can put on it because it's on a flight asset. In this facility, we can monitor up to 2,000 parameters. We also have the capability of measuring up to 8,000 calculated channels. This particular cell is being set up to do icing research. The icing research that we will be doing is that we will be shooting not only ice particles at a live rotating engine, but we'll also be doing what's called mixed phase with ice and water. The reason that this is such an emphasis is that the FAA is changing the rules for certification for icing on engines. With the icing testing, we actually want to cause the issues that they've seen while flying on certain aircraft or certain engines, and so we can better understand the phenomenon and come up with ways to either prevent it, mitigate it, or eliminate it entirely. An engine is basically using conservation of energy. What you do on one side you have to balance that at the other side. So when you bring air into the engine, you're increasing pressure, and from physics, pressure and velocity are inversely proportional. So as I take the air into the compressor, I'm increasing that pressure, I'm decreasing the velocity, and sending that air into the combustor. And once it hits the combustor, I mix it with fuel, give it an ignition source, or spark, which then ignites it. That air now increases in velocity, decreases in pressure. It then spins the turbine, and that air then exits the exhaust of the engine. And because of conservation of energy, even though I'm changing the states of the air or changing the properties of it, I still have to balance it. So by decreasing my pressure at the end, I'm increasing my velocity, which balances the energy.
Wow, that is some pretty amazing technology just to make it safer and more fuel efficient for people to travel by air. Do you think you have what it takes to build a model jet engine?
Teachers, you and your students can get a real feel for how a jet engine works by building your own model. To try this out in your classroom, look for Jet Propulsion by checking out the extension activity for this program on the NASA Explorer School's virtual campus.
Well, that's it for NASA Now. Be sure to visit our Facebook page and leave a comment. We'll see you next time on NASA Now.
NASA Now comes to you from the virtual campus at NASA Explorer School.